Have you ever stopped to think about how your phone knows which way you're holding it, or how a smoke detector can literally sniff out a fire before you can? Well, it all comes down to these tiny little devices called sensors. Today, we're diving deep into a really special type of sensor, the chemical sensor. We're going to find out how we give machines the power to smell, taste, and even feel the world around them on a molecular level. So here's the plan. First, we'll look at the big picture of sensing. Then we'll zoom right into the guts of a chemical sensor to see what makes it tick. After that, we'll check out some real-world examples, including a medical device that's a total game changer. And finally, we'll look at the report card. Yeah, a report card that engineers use to grade how well a sensor performs. Let's get into it. All right, first up, sensing our world. You'll see that a lot of this is really just technology trying to copy what nature already perfected. I mean, our world is just blanketed in these things. You've got them in your phone, in your smart home, in the smoke detectors and gas detectors that keep our cities safe. You can think of them as the silent, electronic nervous system of our modern world, just constantly feeling out the environment and reporting back what they find. Now, this is where it gets really cool. Look at how closely these artificial systems actually copy our own biology. On the left, you've got us. A receptor, like in your nose or on your tongue, sends a signal through a nerve to your brain. And on the right, it's pretty much the exact same setup for technology. A sensing element, the receptor, sends its signal to something called a transducer, which then gets processed by a computer. It's the same fundamental process: detect, convert, and process. So now that we have that big picture, let's zoom in. We're going to go inside a chemical sensor and meet the two key players that make the whole thing work. At its heart, this is really all a chemical sensor is. It's a translator. It takes chemical information, like how much of a specific molecule is in the air, and it turns it into an electrical signal that a computer can actually read and do something with. And this diagram shows you that translation in action. So a sample from the environment comes into contact with that bottom layer, the receptor. You can think of the receptor as the detector. It's designed to recognize a very specific molecule. When it finds it, that interaction causes a change that the next layer up, the transducer, can sense. The transducer is the messenger. It takes that change and converts it into an electrical signal that gets sent off to the electronics. So you can really boil it all down to a simple four-step process. Step 1, the molecules we want to measure, they call that the analyte, show up. Step 2, the receptor, which is tailor-made for that analyte, recognizes it and latches on. Step 3, the transducer converts that little interaction into an electrical signal. And step 4, the computer does the math and gives us a final useful result. The main thing to remember is the incredible teamwork between these two parts. The receptor is the taster or the sniffer. It's the part that does the actual recognizing. And the transducer? That's the messenger nerve. It takes the message from the taster and translates it into electricity, into a language the computer brain can actually understand. Okay, theory is great, but let's see how this whole receptor-transducer team actually gets the job done in a couple of real-world sensors you might have seen. Right, here's a classic pH sensor. You see these in chemistry labs, aquariums, everywhere. See that glass bulb at the bottom? That's our receptor. Its surface is specially made to interact with hydrogen ions, which is how we measure acidity. And the electrodes inside, they act as the transducer. They measure the voltage change from that interaction, which a computer then turns into that final pH number. And check this out. The signal doesn't always have to be purely electrical. This is an optical sensor. Here, the receptor is that big cage-like molecule. When it snags a potassium ion, it causes another part of the molecule to start glowing more brightly. A photodetector then acts as the transducer, turning that change in light into a signal it can measure. So cool. All right, now let's get serious and focus on one of the most important, truly life-saving chemical sensors out there, the blood glucose monitor. For millions of people with diabetes, these devices are an absolute lifeline they use every single day. This is a perfect example of what's called a biosensor, which is just a fancy name for a chemical sensor that uses something biological, like an enzyme, for its receptor. So, the very first glucose sensors were pretty clever, but they had a huge flaw. They needed oxygen for their chemical reaction to work. But here's the problem. The amount of oxygen naturally in your blood is way lower than the amount of glucose the sensor might need to measure. This created what's called an oxygen deficit. The sensor would literally run out of fuel mid-reaction, giving a reading that was dangerously low and just plain wrong. So, for the second generation, engineers came up with this brilliant fix. They took oxygen completely out of the equation and replaced it with a chemical middleman called a mediator. This mediator's only job is to shuttle electrons directly from the enzyme to the electrode. This one little change made the sensor's reading totally independent of the oxygen in the blood. The result? Much more reliable and accurate measurements.
So we know how they work, but how do we know if a sensor is any good? Well, it turns out scientists and engineers have a kind of report card they use to grade them.
And here are the key subjects on that report card. You've got sensitivity, how big is the signal? Selectivity, does it get fooled by other molecules? The detection limit, what's the smallest amount it can possibly find? And then, of course, there's response time, how fast is it? And its stability and life cycle. Basically, how long is this thing going to work properly? Let's just focus on one of the most important grades on that report card, sensitivity. The technical definition is the change in the sensor signal per unit of concentration. But an easier way to think about it is it's the slope of the line on its calibration graph. And this graph shows you exactly what I mean. Along the bottom, you have the concentration of glucose, and up the side, you have the sensor's response. A steeper line is always better. That means you have high sensitivity. Why? Because it means even a tiny change in the amount of glucose creates a big, loud, easy-to-read signal. A flat line would be a terrible sensor. So when you put all of that together, this is kind of the wish list, the holy grail for a perfect chemical sensor. You want it to be tiny, you want it to be cheap, super fast, able to run all the time, incredibly picky about what it measures, and stable for a long time. And that brings us right back to where we started. At the end of the day, a chemical sensor has one fundamental job: to be a bridge. A bridge that transforms the invisible chemical world all around us into a useful signal that we can actually see, measure, and most importantly, act on. And that really leaves us with a final, massive thought. We are building a world that will have trillions of these tiny, powerful electronic sensors scattered everywhere. So the real question is, what new things will we be able to learn? What new information about our planet, about our own bodies, and maybe even about the universe itself will be unlocked when we can finally measure almost anything, anywhere, all the time?